A lot of folks hear biomechanics and instantly picture athletes with sensors strapped on, but the field goes way beyond just sports. So, to kick things off, what kinds of problems are biomechanists actually trying to solve?
It really is broader than most people realize. Biomechanists study everything from how people walk after an injury to how diseases like arthritis change joint movement, and even how to design robotic exoskeletons for folks with disabilities. Basically, if it involves how the human body moves or functions, we're interested.
That's wild. So it's not just tracking movement, but actually helping people regain or improve it. Speaking of tracking, we hear these words a lot: qualitative versus quantitative. Can you break down the difference?
Absolutely. Quantitative data is all about hard numbers like measuring joint angles, speed, or force, while qualitative data dives into personal experiences, such as how someone feels during movement or recovery. Both perspectives are crucial, depending on the problem.
It's funny. Whenever someone mentions qualitative research, I always think of those surveys at the doctor's office. Pick a smiley face if you're feeling good, a frowny face if not. But why do engineers, who love numbers, care about these softer details?
Honestly, those smiley faces can matter just as much as the data from a force plate. Patient satisfaction, for example, is psychological, but directly impacts the success of a rehab device or treatment. If someone hates using a brace, it's not going to help them, no matter how perfectly engineered an island.
That makes a ton of sense. So it's almost like the numbers tell half the story, and the patient's experience fills in the rest. Do therapists actually use these surveys in a measurable way?
They sure do. Physical and occupational therapists are trained to interpret those surveys and even quantify the responses. In rehab engineering, we often combine survey results with motion data to get a complete picture of progress.
That actually reminds me, there's always talk about how hard it is for biomedical engineers to communicate with doctors, nurses, and even other engineers. Why is that such a big deal in your field?
Oh, it's a massive challenge. Biomedical engineering sits at the crossroads of medicine, engineering, and often policy or law. Each group speaks its own language, so miscommunication can lead to real setbacks like misunderstood device requirements or unclear research goals.
So it's not just about knowing the science, but also learning to translate it for different audiences. Is that where the liberal arts and general education come in?
Exactly. Those classes help students build flexibility in how they think and communicate. I've seen graduates thrive because they could explain complex ideas. Simply, sometimes that's what gets their research funded or adopted in clinics.
Switching gears a bit, your path into biomedical engineering is pretty unique, right? You started in electrical engineering in Jordan and ended up leading programs in the States. What was that transition like?
It was definitely a wild ride. In undergrad, I barely touched biology or chemistry. Then, during my master's and PhD in the US, I found myself surrounded by people with deep backgrounds in anatomy or genetics. At first, I had no idea what half the conversations meant.
Oof, that sounds intimidating. Did the engineering mindset help you catch up with all the biology?
Honestly, yes. Engineering is about problem solving, so I approached every unfamiliar topic as a puzzle to break down. Over time, I learned to blend the analytical skills from my electrical roots with the complexity of human biology.
Since we're on the subject of cross-disciplinary work, do you think medical schools should be teaching more biomedical engineering? I've heard you have strong feelings about this.
I'm a huge advocate for it. With AI, robotics, and tech advancing so fast, doctors who don't understand biomedical engineering might struggle to keep up. The healthcare landscape is changing, and blending technology with medicine is now essential.
So you're saying med students need more than anatomy and pharmacology. They need to understand sensors and algorithms, too?
Exactly. Imagine a future where medical and vet schools require core biomedical engineering courses. In 5 or 10 years, grads with that foundation will not only survive, they'll lead the next wave of innovation in healthcare.
It's fascinating how much the field values mixing tech and biology. Do you have students who end up doing research in totally unexpected areas because of this interdisciplinary push?
All the time. Some of my students have gone straight into PhDs with full scholarships, skipping a master's entirely. Their ability to connect dots between disciplines makes them really attractive to top programs.
That's impressive. So even if someone starts out unsure about biology or coding, there's plenty of support and room to grow?
Absolutely. The key is a willingness to learn across boundaries. No one comes in knowing everything. Success comes from curiosity and persistence.
Earlier, you mentioned working on human motion analysis for your master's. How does that actually work? Are you strapping sensors to people and just watching them walk?
Not quite that simple. Sometimes we can't test directly on people, so we build 3D models, think of them as digital skeletons, and run simulations to study things like walking patterns or injuries. We use reflective markers, infrared cameras, and a lot of number crunching.
So you're basically creating a virtual you in the computer, tracking every joint and segment?
You nailed it. It lets us test scenarios like how an ACL tear changes movement without anyone getting hurt, and for complex motions, breaking down the body into segments makes the math manageable.
Speaking of segments, I've heard you describe the body as a multi-segment coupled pendulum. That sounds like something out of physics class. Why do engineers use that approach?
Honestly, the human body is incredibly complex, but as engineers, our strength is simplifying systems to analyze them. By treating each limb as a segment, we can model motion with equations, run simulations, and spot issues that would be impossible to see otherwise.
And I guess that's how you go from theories to practical devices like exoskeletons or prosthetics?
Exactly. Once we have a working model, it's much easier to design interventions that actually work in real life.
That actually brings up a topic that's both exciting and a little unsettling: robotics. You've said you love robots, but you're wary about making them human-like. What's your take on that?
Here's the thing. I think robots are incredible when they solve real medical problems, like exoskeletons for people with disabilities. But building human-like robots just because we can? That raises serious ethical questions. We need to be clear about the purpose. Are we solving a real need, or just inventing tech for tech's sake?
I get that. It's almost like the line is drawn at improving health versus just mimicking humans. Do you worry about robots ever becoming conscious?
Honestly, the idea of machines arguing for their own humanity is something students should think deeply about. If our technology isn't aimed at improving people's lives, maybe we should rethink its direction.
Now, circling back to biomechanics basics, you split the body into rigid, deformable, and even fluid systems. Can you walk us through how each type matters for biomedical engineers?
Sure. Think of rigid body mechanics as bones. They don't bend or squish, so we use them to study lever systems like arms or legs. Deformable bodies cover muscles, ligaments, and tendons, which stretch and contract. Then there's fluids. Blood acts as an incompressible fluid, while air in our lungs is compressible. Both are critical in medical devices like dialysis machines or ventilators.
So instead of learning mechanics in the abstract, students get to see how these concepts really show up in the body.
Exactly, and that's the coolest part. Everything we study in class has a real-world application in health and medicine.
That ties into the classic statics versus dynamics debate. In biomechanics, when do you use each?
Statics comes in when something is at rest or moving at a constant speed, think standing or holding a yoga pose. Dynamics is about acceleration, like jumping or sprinting, where forces and movements change over time.
And all this is more than just theory, right? You actually apply these concepts to real data in the lab.
Absolutely. For example, we analyze vertical jumps using force plates, tracking acceleration, velocity, and more. These principles let us make sense of what's happening inside the body, not just outside.
One thing that tripped me up as a student: what's the real difference between kinematics and kinetics? They sound so similar.
I get that confusion all the time. Kinematics is about describing motion positions, velocities, accelerations without caring about the forces behind them. Kinetics, on the other hand, digs into the actual forces and moments causing those movements.
So if I'm looking at how fast someone's knee moves, that's kinematics. But if I'm asking why it's moving that way, like what force is causing it, that's kinetics.
Exactly. Both are essential for understanding motion and designing interventions that actually help people move better.
Something that really blew my mind was this idea of configuration space, using math to capture how bodies move. How does that work in plain terms?
Imagine each joint angle as its own axis in a multi-dimensional space. If you have 3 joints, you get a 3D space. More joints, more dimensions. As someone moves, their position traces a path, what we call a motion trajectory, through this configuration space.
So instead of tracking dozens of numbers, you can visualize movement as a single path through space?
Exactly. That makes it way easier to compare movements between people, spot abnormalities, or design improvements. We'll be building these models together in class, step by step.
Let's wrap up with something practical. Force plates. You have some in your lab, right? What do they actually measure, and how does that help your research?
Force plates give us forces in 3 directions: X, Y, and Z, as well as the moments, which reflect rotation. Moments are key for understanding things like knee injuries during a sudden change in direction.
So, if you compare athletes, you can see who's putting more strain on their joints during a move?
Exactly, but here's the catch. Never trust a single study's data. We always want to see findings reproduced by different groups before drawing conclusions. That's how we make sure what we discover is actually real.